So I think others are able to see it now. Uh, yes, Gurnur, can you start the discussion? Yeah. Okay. So Gurnur, can start the discussion?
Yes. So today I'm presenting the topic of basis in topology. So the overview of the presentation. In this presentation, we will define the notion of topology and then introduce what a basis in topology is, and then explain its properties and would be going through some of the applications of it. We will also look at the necessary axioms for the existence of a basis and look at some examples of it. So, firstly, introduction to definition of topology. So, a topology on a set X is a collection T of subsets of X such that null and X are in set. The null set and X are in T. Any arbitrary union of subsets in T is in T, and the finite intersection of subsets in T is in T. A set X with a topology T is called a topological space. An element of T is called an open set. So if X is any set, the collection of all subsets of X is a topology on X, and it is called the discrete topology. The collection which consists of X and the null set only is a topology on X, which is known as indiscrete or trivial topology. So definition of basis. In topology, a basis for a topological space is a collection of open sets that can be used to generate all other open sets in the space. Formally, a basis B for a topological space X is a collection of open sets in X such that every open set in X can be expressed as a union of sets in B. A point to note, not every collection of open sets in X is a basis. To be a basis, the collection must satisfy certain conditions which we will discuss in the next slide. So properties and axioms of basis. If X is a set, then a basis for a topology on X is a collection of B of subsets of X such that for each small x belonging to capital X, there is at least one basis element B containing X. If X belongs to the intersection of two basis elements B1 and B2, then there is a basis element B3 containing X such that B3 is contained in B1 and so such that B3 is contained in the intersection of B1 and B2. These conditions are known as the basis axioms. If B satisfies these two conditions, then we define the topology T generated by B as follows. A subset U of X is said to be open if for each X in U there is a basis element B belonging to B such that X belongs to B and B is in U. Note each basis element is it's sorry. Note each basis element is it itself in the element is an element of T. So some examples of basis. So example 1, let B be the collection of all circular regions, interiors of the circle in the plane. Then B satisfies both the conditions for a basis. The second condition is illustrated below. So in the topology generated by B, a subset U of the plane is open if every X in U lies in some circular region contained in U. Example 2, let B be the collection of all rectangular regions in the plane where the rectangles have sides parallel to the coordinate axis. Then B satisfied both the conditions of our basis. Condition 2 is here below. In the case, the condition is trivial because the intersection of any two basis elements is itself a base element. The base B generates the same topology on the plane as the basis B given in the preceding example. So few examples in common topological spaces. So a discrete topology on any set X is the collection of all singleton sets is a basis for the discrete topology on X. Standard topology of R, real. Let R be the set of all real numbers. Let B be the collection of all open intervals. Then B is a basis of a topology, and the topology generated by B is called the standard topology of R. For R2, let R2 be the set of all ordered pairs of real numbers, that is the Cartesian product. Let B be the collection of Cartesian product of open intervals. Then B is a basis of a topology, and the topology generated by B is called the standard topology of R2. So some applications of
Okay.
basis.
One,
Base,
I just have a question here. So when you said a topology is generated by a basis, what do you mean?
So like the base generates the topology.
Yeah, how does it generate the topology? So,
Like,
as you mentioned, topology is a collection of subsets of the set, right?
yes, yes, sir.
Now, the basis is also a collection of subsets of the set.
Yes, sir.
So, my question is that how can you get the entire topology given the basis? How can you sort of construct it? Because you are suggesting that you are using the word generated, right?
Yes, sir. So like like I had no other word. That's why I used
No, no, no.
this.
It is a right word. Okay, Ahorshi has an idea. Ahorshi, go ahead. Tell me what you have.
I don't know like exactly about this, but isn't it because the all singleton elements is it? It's like generated basically means like the singleton is like a generator of this, so we can use all the singleton elements and like arrange them in a way so that we can get all the collection of all the subsets of R of the uh, whatever the space is set X. I
So the singleton sets,
hmm,
when you say singleton, you mean a subset containing one element? Is that what you're meaning?
uh, yes, yeah.
But okay, that could be a basis, but then that would generate the entire power set of the set,
Hmm,
and that would be a topology, but it would be a like a very wide.
trivial.
Yeah, it's not.
Yeah.
Yeah, it is not an interesting topology in that sense. So, for example, what Gurnur is suggesting, the standard topology on R, he is talking about take the open intervals of R,
Hmm,
right?
yeah.
So he this particular basis does not contain the singleton sets.
Hmm,
Naturally, uh, it contains all the open intervals, so it doesn't. The open intervals are not singleton. It will contain infinite number of elements, right?
yeah.
So uh, my question is that these are some of the members of the topology. Now,
Hmm.
using these members as building blocks, how can you create all members of the topology? Okay.
Means like every single topology
No,
of
no,
like
no, no.
whatever.
This basis
So
generates
like
a particular topology. A topology is a collection of subsets, right? It's a
Hmm.
particular collection of subsets of a set. The basis for that topology is another collection of subsets. Now you
Hmm.
want to use this collection of subsets to create the main collection of subsets, which we call the topology, a particular collection. So each topology,
Yeah, because
a set can have multiple topologies, right? You can.
so like
hmm.
but the set of all the open intervals in R like is the basis for a topology on R, because every open interval is an open set, and every open subset of R can be written as a union of like a group of open intervals.
So you are saying that if you start with the basis, you just take
Yes,
union of elements of the basis to
yes,
create
sir.
all the open sets. Is that what you're saying?
Like yes, sir.
Okay. I'm just asking. I don't know. You have to figure it out. So
Yes, sir.
I would ask each of you to think about this particular point, that when you start with a basis, how can you create the entire topology? And in the next session, I will ask some of you to explain this point to me. So you can Google it, find it in a book, find it in Stack Exchange or whatever. I don't care. You can do open chat GPT. I don't care. Just tell me what you have found. Yes or Nisha, go ahead.
So can you please repeat the question once again?
My question is that if you have a basis, so a basis is a collection of subsets of the set X, right? So how can you use that collection of subsets to produce the corresponding topology, which is also a collection of subsets, maybe a larger collection of subsets? Okay, so basis, how can you use the basis to generate the topology? That's my question. Okay, so all right, thank you, Gurnur. I understand you have a few more slides, but
Yes, sir.
that's all right. We can stop your presentation here. You have to think about this point and come back in the next session. Okay.
Okay, sir.
A
Yes, sir.
brief, a brief
Thank you, sir.
clap for Gurnur. Very nice presentation. Very nice. Okay, let's go ahead with Aratrik Pal. Aratrik, do state which class you are in, your full name, and then start the presentation. Okay.
Yeah, so I'm Aratrip Pal, studying in class 9, and I am going to present on the topic Cauchy sequences and completeness in metric spaces.
Sequences and completeness. Okay, very
Yeah,
nice. We are excited to hear you. You can share the screen or share the presentation. So those of you who are joining in now, if some of the Cheenta students are joining in now, um, this particular group of students are working on hyperbolic geometry, and we are learning in the reading portion of this research project. We have to learn topology, group theory, and all those things. So this is a student presentation for that. So Aratrik will be presenting on Cauchy sequences and completeness. Go ahead, Aratrik. Tell me what you have.
yeah. So I start with what is a Cauchy sequence. So a sequence xn in a metric space is called a Cauchy sequence if for any given epsilon, positive epsilon, we can find a natural number n such that for all m and n greater than n, we have d, like the distance between xm and xn is less than epsilon. So essentially, as the first so what this is saying is that as we increase the n, the elements keep on getting closer to each other. So like the first graph shows that the elements are getting closer and closer to each other. And while in the second figure, the elements uh, don't get closer to each other. They don't get arbitrarily close.
Okay.
So that's the definition of a Cauchy sequence.
Mhm.
So now we'll go through a few examples of Cauchy sequences. So we have the sequence xn equal to 1 by n in R. So like for all natural number n. So like it's 1, 1 by 2, 1 by 3 and so on. And it converges to 0. So this sequence is a Cauchy sequence. As the elements of this sequence get arbitrarily close to each other. And the second example is the sequence, like we take the digits of the irrational number pi, like 3,
Okay.
3.1, 3.14, and so on.
Okay.
So this is also a Cauchy sequence, as like the elements keep on getting closer to each other.
Okay.
And in the third sequence, and in third example, we use a metric. We need to use a metric known as the discrete metric.
Mhm.
The discrete metric states that d of x comma x is 0, like d of x comma y is 0 when x is equal to y, and d of x comma y is equal to 1 when x is not equal to y.
Okay.
So a sequence in this metric space, uh, so where all elements are constant after some from some starting from some natural number. So like from some xn, all the remaining elements are constant.
Mm-hmm.
So then the distance will be 0 and it will be a quasi sequence.
Okay.
Yeah, so these were the examples. And now quasi sequences have some properties in metric spaces. So any convergent sequence in a metric space is quasi. So as we saw in the previous examples, like xn equal to 1 by n, this converges to 0, and then the digits of pi 3, 3.1, 3.14, these converge to pi,
Okay.
and both of them are convergence. Both of them are quasi sequences. So this is one of the theorems that any convergent sequence is quasi.
Okay.
Our second property is that any quasi sequence in X is bounded. We can like prove this by taking epsilon equal to 1 in from the definition, and then like proving. You can prove it from that.
Okay.
You can get the maximum value and bounded. And a quasi sequence is convergent if and only if it has a convergent subsequence. So what this means is that if a quasi sequence has a quasi sequence has some subsequence that converges to some element x in some element x, then the whole quasi sequence will also converge to that same element and vice versa.
Mm-hmm.
So yeah, now next we proceed to the completeness of a metric space. So a metric space x comma d is said to be complete
Mm-hmm.
if every quasi sequence in X converges to an element in X, i.e., it has a limit in X.
Okay.
So we proceed to some examples of completeness. So we again use the example of the discrete metric space. So R comma R and the discrete metric is complete
Mm-hmm.
because like every quasi sequence will converge in this metric space.
Mm-hmm.
And then we have a really good example is that all the real number set is complete with the standard. We use the standard this standard metric function.
Okay.
And then an interesting example is that the closed 0 comma 1 real interval with the absolute metric is complete because like so any quasi sequence which we take in this interval, as we know that R is complete, so that sequence also must converge to some element in R.
Right.
Now, any sequence in this interval, if it converges to an element in R, it must necessarily converge to some element between 0 and 1.
Okay.
And a last example is that the open 0, comma 1 real interval with the absolute value metric is actually a non-example because it is not complete. Because the sequence xn equal to 1 by n, which falls in this interval, converges to 0, which is not a part of this interval.
Okay.
Yeah, so this is my presentation on consequences and completeness.
Okay. Okay. That is fine. So that is very nice. So I have a question, Arathrik.
Yeah,
The question is this: that if a sequence is Cauchy and if it is convergent, so we know that a sequence being Cauchy is not necessarily does not necessarily imply that it is convergent, right?
yeah, but convergence implies quasi.
Convergent implies Cauchy, so that requires a bit of proof, which I
Oh,
hope.
so you're asking for the proof that if a sequence is convergent, it has to be quasi.
Yes, and probably you can do this using the picture of convergence that we used in the last session, the funnel picture. Remember that you can, if it has a limit, then you can bring all the terms of the sequence within the funnel after
Yeah,
a set.
and
Yeah.
right, like we take from the fundamental definition of a limit and
So it would be
convergence.
great if you can share that with us. Okay.
I don't have the image with me right
No, no,
now.
that's fine. That's fine. Not now. Maybe in the other session. next one.
Yeah, sure. Like I'll create it on the next in the
Yeah.
next session.
Another thing I have to share with all the kids is that the convergence of Cauchy sequences is one of the most interesting um, points in the history of mathematics. For example, you would have Cauchy sequences of rational numbers which does not converge in the domain of rational numbers.
Yeah, so like we can take the number root 2 and we can find a sequence of rational numbers that converge to root 2, but root 2 is not a rational number, so it is a
Exactly, exactly. So now imagine a world where you do not have irrational numbers. Imagine a world where you do not have irrational numbers. You do not have the knowledge of irrational numbers. You know that every number can be written as a ratio of two integers. Imagine you were living in that world, and Pythagoras incidentally lived in that world, right? Every number can be written as a ratio of two integers. Suppose that's the world you live in. Now you encounter a Cauchy sequence. What is a Cauchy sequence? A Cauchy sequence is this, that roughly speaking, if you move far enough along the sequence, maybe after the 10,000th term, any two members of the sequence will be very close to each other. How close? As much close as you want. So for example, if you do an experiment, suppose you want two members of the sequence, any two members of the sequence, to be 1 centimeter, one by 10th close to each other. Suppose that's the closeness you want. So if the sequence is Cauchy, then if you move far enough along the sequence,
like after a certain point, the distance between any two elements will be less than
1/10. So
yeah.
how far do you have to go? Well, it depends on the sequence. So maybe you have to go 17,000 steps along the sequence. But after you move 17,000 steps along the sequence, if you take any two members of the sequence, maybe they are far apart, I mean, term wise, maybe you take 17,001th point and 1,000,000th point. You take any two elements of the sequence, their distance will be less than 1/10. So intuitively speaking, if you go far along the sequence, it gets squeezed. The sequence is getting squeezed, like the picture of Aratrik. So what you would decide is that if a rational number, set sequence of rational numbers, have this property that it is getting squeezed, then it probably would converge to some point. But your imaginary world where all numbers are rational, you would immediately see that that sequence cannot converge. There are sequences of rational numbers which cannot converge to a rational number.
Yeah.
Hence, you discover the irrational numbers. So there is
like Cauchy sequences are like a way of discovering the irrational numbers.
Correct. Very nice. So this is a little homework for each of you. Go anywhere, go to some book and type in Dedekind. Oh, you cannot type in a book actually, but you can type into the internet, I guess. Dedekind cut. Dedekind cut. Type in that and try to know the story around the discovery of irrational numbers.
So
And
how do you spell it?
Dedekind, Dedekind, cut. So
Yes.
it's one of the most interesting discoveries in mathematics, and I would strongly recommend that you know try to look into it. Okay. uh, Thank you, Aratrik, for that wonderful presentation. A clap for Aratrik. Very nice job.
Thank you.
Let us go to Ahoshi. Ahoshi, introduce yourself and tell me what you are presenting today.
So as I said, can I do mine at the end of
Oh,
the?
yeah. You told me that. Correct. So
Thank you,
let
sir.
me go to Viraj Agarwal actually. Viraj, why don't you introduce yourself and tell me what
Yes.
you have?
So my name is Viraj Agarwal. I'm studying right now in class 11, and today I will be presenting about convergence sequences.
Okay. Why don't you share your presentation, Viraj?
Yes, sir. Is it not visible?
Now it is. Yes.
Okay, I've
Oh,
turned
by
full.
the way, I must mention this one thing. I noticed that Aratrik used LaTeX to produce the presentation. This is very nice. I'm impressed because that's what each of you should be doing. Go to YouTube, learn how to use LaTeX in Overleaf, and produce presentations in LaTeX. It's a great practice, actually. All right, Viraj, please share this presentation.
Yes, sir. Um, okay, so I will be presenting on convergence sequences.
Okay.
So let me start by defining a sequence. So a sequence is an ordered list of elements, typically denoted by an or a sub n, where n is a non-negative integer. So like an is sort of like you can take a1, a2, a3 up till an. That's what non-negative integer index means. And you can specify the position of the element in the sequence using this index. Then how do you define a limit? So a convergence sequence is basically one way to define the limit, where you're using, I think this is the epsilon delta definition, and you're proving that a sequence converges to a limit L. That means I think the diagram, there was an error with the diagram. But the purpose was basically you have like a bunch of points and they are all converging in a certain way, so that as this index n increases, your all an values are coming really close to each other, coming close to this number L. So when you take this an minus L mod, that's basically saying like you're subtracting all the values of the sequence from L and taking the absolute value. It's coming less than this epsilon number. So you can take epsilon to be really small, and then you'll see that all of the numbers in your sequence are sort of like meeting at the point an. To give an example, it's like if you take the sequence of the reciprocals of all the numbers, like 1 upon 1, 1 upon 2, 1 upon 3, you'll see that as you increase n, that number will converge to 0. So in that case, L would equal 0. So these are just some applications to topological spaces. So a topological space is equipped with a collection of subsets, and these are all open sets. Convergence sequence converge to an element, and this applies to subsequences and open sets as well. So a function, and then about homeomorphism, which is also given there. So convergence sequence in metric space. So we all know what a metric space is. I've redefined it over here. And you can see that even in a 2D metric space, you will have like limits where all of the points would converge into one value. And this is one property of a convergence sequence, where if xn converges to x and yn converges to y, then the sum of the two sequences, like if you take that a new sequence and define it as the sum of your previous two, it would converge to the sum of the two limits. And the same goes for the product. So this is proving the limits specifically in a metric space are unique. It may not be true for just topological spaces in general, but it's true for metric spaces. So the idea is that if you have two limits L and M, and you take an epsilon value greater than 0, you can see that as you increase n, the value of the distance function when you take xn and your first limit L will be less than some value epsilon by 2, that is your epsilon from earlier. And the value of the distance function for xn and m will be less than that same number epsilon by 2. And then you can apply the triangle inequality to show that these two L and M are the same. Hence, you can justify that these two sequences are unique. And this just allows us to study them more closely. as the importance of this property. So this is a little bit about discrete topologies. So a topology is discrete if every subset of the space is an open set, and every point is isolated. Every set is a closed set, and the compactness is equivalent to its finiteness. And it's applied in modeling of discrete structures in computer science like graphs and lattices. And this is just a little bit about the real world applications of convergent sequences in general, where you can see in engineering it's used to model the oscillatory behavior and minimize errors in numerical methods. In finance, it is understanding long-term growth of investments and stock trends. And in physics, it's similar, and physics is for waves and energy transfer, as well as in quantum mechanics. This is a little bit about series and convergence, which is about how you take the sums of different series. For example, the first term would be the first term, and then the second term would be the first term plus the second term, which is how you define a series. And about how showing that these three examples of geometric, Taylor, and harmonic are all convergent as well. So this is just a brief example of convergence. Thank you.
Okay, very nice, Viraj. I have a question regarding this. So when you are defining limit, it seems that you are using a distance function, because you are saying that the distance is getting smaller and smaller. It can
Right.
be made. So it seems that the concept of distance is needed to understand the concept of limit.
I guess over here, I've not formally defined like d of x is equal to d of x comma y is equal to x minus y mod. Like, I've not defined it formally, but I guess I've sort of implied it over here, that distance metric of like taking the two terms, subtracting them, and then saying it's less than epsilon. So yeah, I guess it does imply some element of distance.
Okay, so it does. Now I'm interested to know if it is possible to define something like limit of a sequence in a topological space where there is no metric, where
But
there is no concept of distance.
right.
Can you define something like convergence?
I mean, just
No,
visually,
wait,
you can like,
wait.
sorry.
Not now. I would like you to research on this. I'd like you to think about it. Okay? You can read more on this, and then tell more about this. Okay?
So defining a limit in a topological space without using a distance function. And like
Or
this,
finding something like a limit. Something like a limit, because clearly the definition of limit that you're using, you have to use that modulus an minus l.
yeah,
So modulus here is the distance functions. In
right,
fact, you are using the, since everything is, you are assuming everything to be real numbers, therefore you can use an minus l modulus of that. If it was not a real number, in the world of real numbers, if it was any topological space, metric space, then you would have used d of an comma l, right?
right.
Distance between al comma l. So it seems that to make the definition of limit, you first need to assume that this is a metric space. There is a concept of distance in that space.
Yes, I understood your question.
Yeah. So my question is that if it is possible to invent something like limit or convergence in a space where there is no definition of a distance. Okay, so think about it. But thank you, Viraj. What excellent
Thanks.
work. Okay, good work. Okay, next let's go to Krish Agarwal. So Krish, why don't you introduce
Yes,
yourself and then share the screen?
yes.
So is the screen visible?
Yeah, it is visible.
So my name is Krish Agrawal and currently I'm studying in standard 12.
Okay.
So the topic for my presentation is dense sets. So what basically is a dense set? So if we have x comma t to be any topological space, then a set A, which is a subset of x, is said to be dense in X if the intersection of A with any open set U of T is non-empty. So to quote it mathematically, we can say that for all open set U belonging to T, the intersection of A and U will never be phi. So if we look at the diagram, we have the set X and A is any subset of it. Now, if we look at the points the distribution of the points in the set A, it is pretty scattered. Like the distance between any 2 points is very low. So if we draw any open set U, we will always point some point which is common to both U and A, which will like the size of U does not matter because we can change the radius of the open ball according to our convenience, but we will still find some element which is common to both A and U. So that will make A a dense set in X. So now closure of a set. Now let S to be any metric space. Then X is a point of closure. If for all r greater than 0, there will exist some point P belonging to S such that d of x comma P is less than r. Now if we consider three scenarios over here, in the first scenario, X will not be a closure point because we can draw infinitely many open balls around S, which won't intersect S. Like two of them are shown here. In the second diagram, X is itself a part of S. So no matter how small or big the open ball becomes, the intersection of the open ball and S will never be phi. There will always exist some element P. And similarly, if we look at the third diagram, we will see that some of the open balls around X give us a will give us some point P which will belong to S. But if we look at the yellow open ball, it will not give a point P which will belong to S. So that's where the point for all r greater than 0 comes in play. Like we need to find like the point X must be such that for all r greater than 0, there must be some point P which will belong to S. So will be the same.
Can I interrupt?
Yeah.
Can you explain the third situation again?
Okay. Sir.
The third diagram,
Yes, sir,
third
yes.
picture, yeah.
So in the third picture, we have the set S and the point X.
Mm-hmm.
Now, now the definition of the closure set is if we draw open balls around open balls around X with any arbitrary radius, all of them must have some point S in them. Like the intersection of the open ball and S must contain some point P.
Mm-hmm.
Now, if we look at the open ball the yellow open ball, it will not intersect S. So like there won't exist any P belonging to S.
Yeah,
So
but
we can
what
say
is
that
the difference of this situation with the first situation? Because in the first situation, it seems to me that if you take a larger ball, it would intersect the white region, right?
yes, so like if we create another concentric ball,
Yeah.
it will.
So what is the difference between that one and this one?
No, so there is no difference between them.
Actually, what you want, I think what you would want to say for the third situation, there is actually a third situation. What you would want to say is that the point itself in the third situation, the point itself is outside the set, but any open set containing that point will intersect the white region. So how can that happen? Well, it can happen in many ways. If in roughly speaking, if it can happen if the point is at the boundary.
So like it lies on the circumference.
Exactly.
Yeah.
Maybe the circumference is not part of the open set or white. The circumference, the white region is only interior of the disk. Now you take a point on the circumference. Of course, that point is not inside the set. But if you take any open set around that point, it will intersect the white.
Okay.
So,
Yes, sir, got it.
so it is in the closure of the white, but it is not a member of the white.
Yes.
Okay. So there, I mean, the idea, the intuition of boundary may not be necessary. For example, if you take the rational numbers in the set of in the set of irrational numbers. So suppose you have the set of irrational numbers. Now, if you take any rational number, that would be in the closure of the irrational numbers. The rational number itself is not an irrational number, so it is not in the collection of the irrational numbers. But that point, if you take any radius ball, any interval containing a rational number, it will contain some irrational numbers, right? So it would intersect the irrational numbers. So again, rational numbers are dense, are in the closure, are in the closure of the set of irrational.
Irrational. Yeah.
Okay, yeah, continue please.
So now if we look at some equivalent definition of dense sets, so the closure of A in X is equal to X, then we can say that A is dense in X. And if we look at the intuitive definition of a dense set, so a subset A of a topological space X is said to be dense in X if every point of X either belongs to A itself or is arbitrarily close to a member of A. And the third definition can be the interior of the complement of A is empty. That is, int of X by A is 5. Now, if you look at some examples of dense sets, rational numbers and irrational numbers are both a dense subset of real numbers, because if we choose any rational number and create an open ball around it, we will always
Yeah, are you speaking?
so like yes sir. So if we have if we choose a rational number and we create any open ball around it, then its intersection with like that open ball will contain some real number.
Yeah.
So the intersection won't be 5. So that will make rational numbers dense in real numbers. Similarly, the same argument can be said for irrational numbers. Now, if we look at an example in R2, so there is a topological space R2 comma tau. Now, if we consider the subset A to be A to be all the points xy which belongs to the R2 and xy is not equal to 0. Now, xy is not equal to 0 implies that both x and y are not 0. So we can neglect the x-axis and the y-axis. So this will mean that A will contain all the points which will not belong to the x-axis and will not belong to the y-axis. So I have taken some scenarios, like if we create an open ball and it won't intersect both the axes, then the open ball is wholly contained in A, so it will be dense in A. And if it cuts the axis at more than one or infinitely many points, then also we can say that irrespective of the size of the open ball, we will always get some element of the open ball which is common to A, so their intersection won't be 5. So now
I think that would be very nice. I mean, we can stop out here. How can you? Did you create this picture, or you got it from somewhere?
so like I created the graph in Desmos.
Oh, Desmos. Okay, very nice. It looks nice. Okay, thank you, Viraj. Nice work. A clap for Viraj. Very good work. Okay, Next, I think we have Onisha. Onisha, go ahead and start the presentation, please. And then you can also let us know about your. Okay. Yeah, I think you have to unmute yourself, right? Okay. Okay, I can see on Nisha's slideshow.
So my name is Anesh Mondal. Currently, I am a first year student undergraduate. Uh, Today, I am going to talk about limit and cluster points.
Okay.
First, I will give you definition of limit points in metric space. Let X be a metric space and E be a subset of X.
Mhm.
Then a point Y belongs to X is a limit point of E if and only for every R greater than 0 we have that the boundary set of the open wall of Y intersection of E is not phi. I've tried to show it using a diagram. So here I have taken 3 points A, B, and C from X. So in first case, we can see that if we take A, then the boundary set of A has no common point with E. So A will not pick a limit point of E. But B is itself contained in E and C has also some common part with, so there will be limit points. Uh, Examples of limit points in metric space. The set of all limit points of Q in R with the Euclidean metric is R. So the proof is if we take an element from Rx, then for any R greater than 0, we have that the open ball V x R is equal to the every element Y such that the distance function x comma y is less than R. Now, what is the distance function? That is equals to mod of x minus y such that mod of x minus y is less than R. What does it mean? That means that x is lies between y minus R and y plus R. So, from the density of rationals, we know that given any two real numbers, we can always find a rational number between them. So, by density of rationals, we can say that for any x belongs to R, for any R greater than 0, we have x minus R minus x plus R union Q is not equals to phi. Hence, we can say that every real number is a limit point of Q since x is an arbitrary point. Okay. Now I will give you sequential and topological definition of limit point. Let X be a metric space and E be a subset of X. Then a point X is a limit point of E if and only if there exists a sequence Xn in E such that Xn converges to X. So this sequential definition is not valid for arbitrary topological space. I will give you the topological definition. Let E be a subset of X. E be a subset of a topology space X. Any point X belongs to X is said to be a limit point of E if and only if every element, every non-empty open set that contains X contains a point of E. So a point to be noted is that every definition is same actually. Okay. Now we will talk about cluster point or accumulation point. We say that X is a cluster point or an accumulation point of a set E if for each R greater than 0, the set Bx or union E contains a point other than X. Well, the difference from limit point is that in the limit point, we have seen that limit points also contain X, but in cluster point, X will not be in the set, or X will not be the common point of Bx R union E. I've shown that with an example that if we take an interval -1, 1, -1 by n, 1 by n, is a subset of R, yes, 0 will be the only cluster point of A because 0 will never be the part of A. If we small it down, that -1 by 1 is -1, 1, then -2, 2, minus half, half. In this way, if I go through this, then 0 will be the only cluster point. Okay. I have shown that difference between limit point and cluster point that every point of Z is a limit point of Z, while Z has no cluster point. Well, if I take P to be an cluster point of Z, then P has to be belongs to Z. But the open set, if we take now the open set P minus half comma P plus half, then Z union P minus half comma P plus half minus P, since P cannot be contained in the boundary set with open ball. So that will be pi, because the common element here will be P. So therefore Z does not have a cluster point. In the contrary, if we can say that, but for limit points, Z will be the Z and the subset P minus half comma P plus half will be P. So P will be a limit point of Z. So in this way, we can say that every point of Z is a limit point of Z, but Z has no cluster points. Thank you.
Okay. So I really like the fact that you know you actually explained the difference between limit point and a cluster point. When I first encountered this idea of limit point and cluster point, um, it was a bit confusing because they seem to be similar, at least from the definition point of view. So, what I would suggest each of the students is that you should try to look up the definitions of limit point and cluster point one more time at your space and try to convince yourself the difference between the two definitions, the limit point and cluster point. Okay, so would be very important. Yes, Anisha, go ahead.
So actually, I have looked into many different parts. So some books say that limit points are cluster points are same, but some says that limit points and cluster points are different.
Right. I mean, it depends on the terminology. So, limit point, cluster point, accumulation point, there are different terms people use. One book that you can follow for this is Baby Rudin. What's the name of that? I think it's called Mathematical Analysis by Rudin. So just type.
Yes, sir.
Yes, sir. Analysis.
So
By Walter Routine.
yeah. So that is like the authentic reference for this sort of stuff. So you can check Rudin. If Rudin says they are different, then they're different. So yeah, but it's a very nice presentation on Nisha. Clap for you. Very nice work. Okay, so we are only left out with Ohorshi, but what I would suggest is since Ohorshi's presentation is not complete, I would give him a little bit more time. In the next session, we will start with Ohorshi's. Usually, I wouldn't have done it, but let's say Ohorshi cleared BMO, or this is an one-off thing for that. Let's suppose if some of you clears INMO, then you will also get one exception ticket, I guess, from this research project. The reason I am a bit strict in this kind of scenario, you have seen how many students I have simply let go from this project, because you understand that the kind of thing that we are trying to pull off, it would require an extra degree of seriousness, right? It's not, it won't be easy. So I'll just let Ahoshi present the next time. Yes, Ahoshi, go ahead.
So actually, I'm almost done. I only wanted to leave them with like some exercises, some like basic questions. So
Oh,
I
okay.
like I'm 95% done. So if you want, like I can share it right now, and I like whatever extra bit is remaining, I can share it next lesson.
No, that's all right. You can just share the entire thing in the beginning of the next discussion, okay? And I would really appreciate Shomodip's time. Shomodip, thank you for your time as a teaching assistant of this program. And just talk to Shomodip. By the way, Shomodip, did you talk to Anika? Did you get a chance to talk to her?
No, I did not get a chance to.
Okay. Just sit with her
Yes.
and explain some of the initial concepts. Just Anika, make sure that you are working in Shomodip's time. Talk to him.
Yeah.
Okay. And you can also talk to other kids in the group. All of them are really good. Just talk to everyone and try to get the material that you have not that will bring you up to speed. So we want to talk about hyperbolic geometry and metric spaces and stuff like that, and group actions on hyperbolic planes. So ton of interesting stuff. But we have to start with the basics of metric spaces, topology, group theory. That's exactly what we are doing. All right. Thank you, all of you, for joining in today. I really appreciate the work that you have put in. Excellent. If we keep on pushing for the next 5-6 months, I think we can get something nice out of it. All right. Bye. Take care.
Thank you very much.
Sir, bye.
Yeah.